You know, when you picture a rocket launch, your eyes are immediately drawn to that massive, chaotic pillar of fire and smoke just billowing out from underneath the vehicle, right? It's a total spectacle of raw, untamed power. But honestly, creating a massive explosion is actually the easy part. The true unsung hero of a rocket engine is the component that takes all that wild, chaotic explosion and completely tames it, turning it into highly directed upward thrust. Welcome to this explainer. Today we're going to unpack the brilliant engineering behind rocket nozzle expansion.
Okay, so let's dive into the core mystery here. Inside a rocket's combustion chamber, propellants burn to create gases at absolutely mind-boggling temperatures and pressures. I mean, we're talking about a massive amount of thermal energy. But here's the thing. Heat and pressure alone, they won't lift a rocket off the pad. To actually overcome gravity, all that energy has to be transformed into kinetic energy. Specifically, staggering directional speed. So how exactly does a rocket engine pull off this ultimate vanishing act? How does it turn stationary, super high pressure into raw, supersonic motion?
To answer that, here's our flight plan for today. 1. We'll look at the engine's unsung hero. 2. The anatomy of a nozzle. 3. The thermodynamics of thrust. 4. The atmospheric challenge. 5. The factors affecting expansion. And finally, number 6, why nozzle design actually matters. All right, let's jump right into section 1, the engine's unsung hero, from chaos to thrust. The secret to the whole thing really lies in something called nozzle expansion. This is the process where hot combustion gases expand from a really high pressure region in the combustion chamber down to a much lower pressure at the nozzle exit. And this isn't just about opening a valve and letting gas escape, no way. It's a highly controlled, very specific physical reaction. The ultimate goal, to maximize exhaust velocity. Think of the nozzle as the ultimate pressure-to-speed converter. It's taking that raw thermal energy and transforming it into kinetic energy with as few losses as absolutely possible.
Which brings us to Section 2, Anatomy of a Nozzle, or as it's often called, the de Laval journey. Let's actually track a single gas particle's incredible high-speed journey through this hardware. First up, it enters the convergence section. Here, the walls of the nozzle literally squeeze inward, and that accelerates the subsonic gases, shrinking the area and cranking up their Mach number. Then, boom, it hits the throat. This is the absolute narrowest point of the whole engine. Right here, the mass flow maxes out, and the gas hits exactly Mach 1, the speed of sound. Finally, the particle bursts out into the divergence section. The area drastically widens, the pressure absolutely plummets, and the velocity goes fully supersonic. That is what generates our crucial thrust.
Moving right along into Section 3, Thermodynamics of Thrust. Let's talk about the physics of speed.
Notice the brilliant inverse relationship happening here across these three regions. Inside the combustion chamber, pressure and temperature are incredibly high, but the velocity is actually quite low. Then, as we hit that narrow throat, the pressure and temp begin to drop, while velocity hits sonic speeds. By the time we reach the nozzle exit, pressure and temperature are at their absolute lowest point, but the velocity, it is completely skyrocketed to supersonic speeds. To gain all that massive kinetic speed, the rocket literally has to bleed off heat and pressure. It's a very direct, highly calculated trade-off.
Now, engineers quantify all of this geometry using something called the expansion ratio. Put simply, it's just the ratio of the nozzle's exit area to its throat area. A larger ratio generally means higher exhaust velocity and much better efficiency. But, there's a huge catch here. You can't just build an infinitely massive nozzle bell. Giant expansion ratios really only work perfectly in the total vacuum of space. And honestly, that introduces one of the biggest headaches aerospace engineers have to deal with.
Which leads perfectly into Section 4, the atmospheric challenge. The constant battle with altitude.
So, depending on the atmosphere outside the rocket, a nozzle's expansion falls into one of three states. The absolute Goldilocks ideal is a correctly expanded nozzle. This is where the exit pressure perfectly matches the ambient atmospheric pressure outside, giving you maximum efficiency. But if the exit pressure is higher than the ambient pressure, we call that underexpanded. And if it's lower, that's overexpanded.
Let's actually pit these two non-ideal scenarios against each other, because it really highlights why this is such a frustrating engineering trade-off. In an underexpanded nozzle, which is super common at high altitudes, the gases literally continue to expand outside the nozzle itself. Because this expansion is happening out in the open, not all the pressure converts to kinetic energy. You're basically just wasting valuable thrust potential, losing it right out into the void. On the flip side, an overexpanded nozzle, common at low launch altitudes, is genuinely dangerous. The heavier atmospheric pressure forcefully compresses the exhaust plume inward. That can cause flow separation inside the nozzle, creating these intense shock waves, decreased thrust, and severe structural vibrations that can legitimately threaten to tear the entire vehicle apart.
So what's the main takeaway from all this? Well, basically, Earth's atmosphere just doesn't cooperate. Pressure is incredibly high down at sea level, but it's practically zero up in space. Meaning, a nozzle perfectly tailored for sea level is going to be painfully inefficient once it reaches space. But conversely, a massive space-optimized nozzle might literally shake itself to pieces from overexpansion right there on the launch pad. Let's look at how we fix this in Section 5, Factors Affecting Expansion, Tuning the Engine.
Let's rapid fire through the 5 critical parameters engineers can actually manipulate to solve this puzzle. First, increasing chamber pressure. That increases the pressure ratio across the nozzle, giving you higher exhaust velocities. Second, tweaking that expansion ratio we talked about improves the overall propulsion efficiency. Third is ambient pressure. Naturally, a lower ambient pressure outside the rocket just improves overall nozzle performance. Fourth, we have propellant properties. Things like the molecular weight and combustion temperature of your specific fuels strongly influence how those gases are going to expand. And finally, number 5, the nozzle geometry itself. The precise mathematical profile of that bell curve dictates flow smoothness, boundary layer behavior, and helps prevent those extremely dangerous shock waves.
And that brings us to Section 6, Why Nozzle Design Matters, the final payoff.
At the end of the day, mastering this incredibly complex physics directly dictates whether a mission succeeds or fails. A highly efficient nozzle gives you higher exhaust velocity, way greater thrust, and massively improved specific impulse. That means better propellant utilization, basically a lot more bang for your buck. And when you use fuel more efficiently, you can significantly increase your payload capacity. This is exactly how we're able to get much heavier satellites into orbit or send those super complex rovers millions of miles deep into the solar system.
But, aerospace engineering never stands still. To completely beat this atmospheric challenge once and for all, engineers are actively looking beyond the fixed, rigid metal bells that we use today. The future is all about adaptive, altitude-compensating nozzles. Just imagine a rocket nozzle that can physically adjust its own geometry mid-flight, maintaining absolute peak efficiency from the heavy air of the launch pad all the way up to the total vacuum of space. It is a real game changer.
It really is a thrilling frontier in rocket science. We figured out how a carefully shaped piece of metal can transform chaotic, explosive thermal energy into the precise kinetic speed needed to conquer gravity. But as we push deeper and deeper into space, designing heavier payloads for much longer journeys, you have to wonder, what new shapes and crazy dynamic adaptive systems will we invent next to fully master the chaos of combustion? The nozzle really is the unsung hero of spaceflight, and its evolution is far from over. Thanks so much for joining me for this explainer, and hey, keep your eyes on the skies.